Hi guys. Well, today I want to talk about the derivation of some enzyme kinetics. Excuse me. Yeah. So, to begin, when you think about enzymes, what do you usually think of? Well, you will think of, if you are familiar enough with the chemistry of it, you think of it being a biological catalyst, and you're not wrong. So, in such a reaction, you'll have a substrate. Let's say you have a substrate, which we just call S, and then a substrate is, something like starch, or can be starch, can be protein. These are like the raw ingredients. The fancy word, the correct word for it, is called substrate. So a substrate, which is the raw material, undergoes a catalytic reaction with the enzyme to form some product P. And if you have done your biology before, you'll know that there are enzymes that can convert starch and proteins into, let's say, simpler molecules or substances. That is usually the case with digestion. So just to refresh your memory here, we have this amylase which converts starch, and we have protease. Don't look at the other sides yet. We have protease, we have amylase that converts starch molecules into, maybe simpler sugars, and protease which converts protein into, probably some shorter chain of proteins or amino acids. And enzymes usually operate by a lock and key model, where you have the enzyme specifically catered to a substrate, and this will react to form an enzyme substrate complex, which you just call this ES, and the reaction will proceed and will form the enzyme and some product. And well, you have many such reactions that produce this product P, and of course it can go backwards as well, as is the case in glycolysis, where you have many kinases which I believe you can either kinases or what do you call that, the isomerases, which can convert glucose and the derivatives of glucose into different forms. Okay, so there are many kinds of enzymes for many kinds of reactions. Each are very specific to the each enzyme is quite specific to each reaction. So how do we conceptualize an enzyme reaction? Well, according to what we have seen just now, this lock and key model, we can visualize the enzyme and substrate combining to form the enzyme substrate complex as the first step. So don't look at this part first, just this part. So the enzyme and substrate form an enzyme substrate complex, and this shows that it is in equilibrium. Okay, so in equilibrium, once this thing forms, it will tend to react and form the product. Of course, this will be in equilibrium as well. So there's a forward and backward step, which I will just call it the second reaction. Okay, hope things are okay so far. Yeah. So, how do you kind of derive these kinetics? Because these are like so-called two steps, right? Yeah. And of course, in this assumption, how do we even start? So let's take a look. Let's take a look at some balance equations. Firstly, we know that P is our product of interest. So we want to look at the rate of formation of P. So this is what we want to focus on first. We just call dP dt, the change in concentration of P with respect to time, the product. We just call this term V, which is the reaction rate. And what is this equal? Well, if we assume this is a first order reaction, we can assume this. It is equal to K2 times ES. And of course, there is a backward rate as well. There's a backward rate. However, for experimental purposes, we kind of want to do the initial rate experiments. what are these initial rate experiments? What does it mean? It means that, during the initial stages of the enzyme conversion, the concentration of P is so small that this can be essentially considered a forward reaction. So this is what we see here. So under initial rate conditions, this holds true. So the rate of formation of P is K2 times ES. If it's not initial rate and the product concentration is pretty high, you have to include a backward reaction step. Okay? Now, and you might also have this question, if you have noticed this reaction, why isn't there an EP complex? There's an ES complex, which is the enzyme and substrate complex, but shouldn't there be something like this as well? E and P. Shouldn't it be like that? Well, you could suppose that such a complex happens, but you see, when the product is formed, it may form a different shape. So this, as soon as a product formed, maybe the enzyme is designed in such a way that it dissociates extremely quickly, so that the residence time, or the existence of this EP is so small that you can almost neglect it. So maybe you have something like this, and then you have something like this. But this step is so fast, you can almost consider the whole. You almost consider that the dissociation is so fast that you can assume that as soon as P forms, it just immediately dissociates. So that's the assumption of this equation here. And for most enzymes, I suppose you could take that, you could assume make this simplifying assumption. Alright? Anyway, let's move on to our second set of equations. So yeah, hope you've understand so far that why we want to write this first equation steps is because we are interested in the rate of formation of P. So then we find this. So now that we have this step, and let's say you want to discover this enzyme kinetics using some kind of initial rate experiment. So we just write K2 to the ES, K2 times ES. That will form the rate of formation of P. So K2 is the rate constant for this second reaction in the forward direction. We ignore the backward direction because we assume this P is very small, so that the backward reaction is just negligible. However, there is one problem with this. We don't know. Do we know the concentration of ES? We probably don't, right? So how do we find the concentration of ES? So that becomes another problem. So what do we have to do? We might have to consider the equilibrium of ES. So we have to consider this reaction and this reaction. To find the concentration of this, we have to perform a mass balance over ES. And let's take a look at the ES balance then. And let's see what is inside. Okay, so dES dt, okay, just cover this up. dES dt, the rate of accumulation of ES, is equals to the negative rate of consumption. That means, of course, if it's consumed, that means there is less ES around, so you have to put a minus sign. And of course, we have to include the equilibrium reactions as well. Now you might wonder what this is, but I'll explain it in a bit. Okay, so anyway, the forward rate of reaction for the equilibrium reaction, I'll just call it K1. K1 into E into S. That will form this forward rate of reaction. Okay, so forward rate, K1 times E, concentration of E, the enzyme, the free enzyme anyway, and the concentration of S. Okay, and the rate of the backward reaction will be negative K minus 1. This is the backward reaction, where this ES reforms the enzyme and substrate separately. So this is the K minus K1 inverse. So I just put K subscript minus 1 times the concentration of ES. So now you have equations in ES, and you kind of measure this, you can measure this, you can measure this, and you can measure this. And when you can measure each of this, and ES is your only variable, you can do some differential equations. You should be able to solve the evolution of ES with respect to time. One problem though, you may know the concentration of substrate, the concentration of substrates within your experiment, assuming it's very large and all that. However, you do not always know the instantaneous concentration of enzyme. So now we have another problem. So how do we do the concentration of enzyme? How do we consider this concentration of this enzyme? So to do that, again, we have to do another species balance. We call this enzyme balance. Okay, so what goes on in the enzyme balance? Okay, so let's say we have three terms here. You have this term, let's talk about, okay, the total concentration of enzymes at the start, the initial concentration of the enzymes. This is very easy to measure. It is, given to you, or you can set it yourself in the experiment. Okay, so this total concentration of enzyme is equal to the concentration of enzymes that are attached to the substrate and the concentration of free enzymes. Okay, so that's essentially, of course, your enzyme balance. So the total enzymes, or the initial enzyme concentration, equals to the ES plus E. Okay, hopefully things are clear now. So of course the initial rate is the initial concentration of free enzymes is the total concentration, because you haven't added your substrate yet. So if you haven't added your substrate, this E naught is the total concentration of E. Okay, so this is the total, right? Okay, anyway, so this is your initial enzyme concentration, which just happens to be the total enzyme concentration when you have it in the initial phases. Now, you still have another problem. With this, you kind of revert back to the second equation, because now you have another unknown, which is ES. You haven't even found out what that is yet, and you still have E. And this is the enzyme balance over to find this E. And so what do we do? How can we narrow down the number of variables? Well, there are two assumptions you can take. One is called there are two assumptions, two assumptions you can make to simplify your equations. Well, one assumption is that the second equation is rate controlling. That means the second reaction here is the slow step. Okay, if the second equation is the slow step, then ES is always set at equilibrium. Now, because the second equation is always so slow, equilibrium can be very easily reached. And if equilibrium can be very easily reached, then the concentration of ES is always at equilibrium, and you can measure it with the equilibrium constant. Now, this is what people call the rapid equilibrium approach. Okay, and there are people who have actually invented the methodology. I believe their names are Henry, I think Michaelis and Menten. It's a Michaelis-Menten kinetics. Okay, and of course, this is what they usually assume, which is the rapid equilibrium is all reached. Now, that's under the assumption that the second equation is slower or rate controlling. Now, what about the case where the second equation is not the rate controlling, but instead the first equation here is rate controlling? So this is the slow step, this is the fast step. Under that assumption, what happens? So just to clarify again, our first assumption is where this step is rate controlling and this step is very fast. The second assumption is that this step is very fast and this step is rate controlling. Under that, what happens? Okay, so you just ignore the numbers first. Alright. Okay, so under the second equation, we have this situation. So this equilibrium constant becomes rate controlling and the second equation doesn't become rate controlling. So what happens here? Well, you find that compared to the first one where this one is controlling, this one always reaches equilibrium, right? Where this is very slow, this step is very slow. Therefore, this always has time to reach equilibrium. But if the rate at which the equilibrium is formed is very slow, this step becomes not fast enough and this step becomes the fast step. Now, if this is not fast enough, equilibrium obviously is never reached. But then you will have the situation where this step, this fast step, is being controlled. The rate of this fast step forward is being controlled by the rate of this step forward. So after the situation kind of continues for a while, it kind of reaches a pseudo steady state where the forward rate of reaction here is also approximately equal to the forward rate of reaction here. So under the situation where the forward rate of reaction is approximately equal to the forward rate of reaction here, the net forward rate of reaction is equal to the forward rate of reaction here, we have something called the pseudo steady state assumption. Pseudo steady state assumption. Okay, so that is what happens. These two assumptions, the equilibrium, rapid equilibrium assumption, where you assume the second step, second reaction is controlling, and the first, this pseudo steady state assumption, where it is assumed that this step is controlling. These are the two basic assumptions you can use to simplify your equations. Now, thanks for watching. This is only part 1 of the derivation, where you have to set your problem up really nicely before you do your math. So in the next video, we want to talk about doing the actual math, where you actually derive your equations. So thanks for watching. See you in the next video.